Okay, in this video, we're going to be talking about section 4.3. We're talking about the logarithmic functions. In the last section, we learned about the exponential function, and in this section, we learned about the logarithmic function, and what we know from section 4.1, we learned about what an inverse is. So these two are inverses of one another. A log and exponent are just inverse, so they're very related. Sort of like multiply and divide are related, add and subtract. We've got these logs and exponents. So when we think about solving an exponent, you think, for example, 5 squared, and I feel like we're all usually more familiar with that idea, how to use an exponent. So finding the answer to an exponent, we call that doing exponents. When we're trying to find the exponent needed to get 25, when we're looking for the exponent, that's the essence of working a logarithm, finding the exponent needed to get that answer. We don't write it like that, though. We have a notation for logs. We write it as log base 5 of 25 equals what? So again, the base of the exponent, base of the log, this is called the argument of the log, and the answer to the log is the exponent, finding the exponent. All right, if you're following along in your handout, we're going to practice rearranging some of these to get the hang of that. So if we were doing what is log base 2 of 16, that means 2 to what power is 16? We could say 2 to what power is 16. We could work, some of these we can just work out, they come out even. We'll get to some that we'll need to use our calculator on in just a little bit. But let's practice some nice even answers. Log base 3 of 27 means 3 raised to what power to get to 27? So 3 cubed is 27. Log base 8 of 1/64. So 8 squared is 64, but because it's in the denominator, it had to be a -2 exponent. So 8 to the -2, and again, check it on your calculator. 8 to the -2. -2 means write it as 1 over 8 squared. The negative exponent moves it to the denominator. Log base 5 of 125. 5 to the 3rd is 125. Let's see, log base 10 of 1. 10 to what power is 1? Oh, I think I skipped 1, but okay, moving on. 10 to what power is 1? That will be 0. Check it out. Anything to the 0 power is 1, no matter what the base. And this we can actually do on our calculator. Base 10 logs, our calculator does directly. We have 2 buttons on our calculator, a common log button. So base 10 is the LOG button. You can find that on your calculator, so check that out. Just hit log 1 equals. You should be able to see that. Okay, log base 10, another base 10 log. So to do this on your calculator, you just hit log of 10. You don't have to subscript it. It's the understood when you're doing base 10s. But log base 10 of 10 should be 1. 10 to the 1st is 10. How about log with nothing subscripted of 1,000? So if you see nothing in the subscript, it's understood to be 10. So 10 is the default, the common log, base 10. So 10 to what power is 1,000? 10 to the 3rd is 1,000. Right. So that's what you see listed at the top of the next page. We talk about what's on your calculator. Okay, we have 2 log buttons on our calculator. We have the LOG, regular log button, which means log base 10, and you also have an LN button. Let's locate those. Let's take a minute, find those on your calculator screen. Okay, I had to find my calculator, so sorry about that. So y'all maybe have had time to find yours now. But I'm using my iPad. I've upgraded here, so maybe you can see it a little better. But when you hit the regular log button, let me clear this off. When we do log, for example, log of 10, just a common log, log base 10 equals, that should be 1. So we can do the log base 10 of anything. We can do log of 100. I'm doing some that just come out nice and neat. Log of 100 should be 2 because 10 to the second is 100. Log of 1,000, log of 74. What's log of 74? That means 10 to what power is 74. So that one's not a nice answer. So they won't always come out even. And then the ln, when we do ln of e, for example, let's plug e in there. ln, where's my e? E button. I know I do this for a living, but it takes me longer to find these little buttons. Maybe you guys are finding it quicker. It's over the divide sign. Okay, ln of e. Okay, ln of e should be 1. So whenever we do ln, it's understood to be base e. So if I did ln of e, that would say e to what power is e. That's why that's 1. All right, so you have some practice problems. I'd encourage you to pause the video and check these on your calculator just to get used to this. And then I'll reveal the answer in just a second. Now the ones that don't come out even, you might have a question of what should we round to, and it should be specified in your homework to round to the tenths or the thousandths or whatever place value is requested, because the ones that don't come out even are irrational numbers. So when we do log of 54, I get a long decimal, 1.73239. It goes on and on and on. It is an irrational answer when it's not perfect. It's sort of like radicals in the exponents. Well, in the world where we had fractional exponents, that's radicals, and they're irrational. If we do the square root of 3, a non-perfect radical, it's also irrational. It's an irrational number. Pi is an irrational number. E is an irrational number. Non-perfect logs, like log of 54. Irrational numbers mean they're still real. They're still real numbers, but they don't come out neat where they can be expressed as a fraction. You can't convert these to fractions. Irrational numbers never repeat. They never terminate. So we have to round on these. It'll need to tell us. So for example, if we were rounding to hundredths, this is tenths, hundredths, thousandths, so on. So hundredths, the 2 would not round it up, and we'd write 1.73, depending on what you're asked to round to. All right, moving on, log of 0.01 is -2. Log of 10 should be 1. How about ln of 54? ln of 54 is, I'm going to do the squiggle line again. When it doesn't come out perfect, I'm having to round. 3.98898 and so on. So to hundredths place, it would round up to 3.99. It's almost 4. How about ln of 0.01? That is -4. We'll say 61 to the nearest hundredths place. All right, so a little practice with that. The next thing you might be wondering, well, what if it's not base E or base 10? What if we're doing a base 2 log or a base 7 log? How will I do, for example, ln a base 7, or let's do log base 7. Here's one we could do in our mind. We could do log base 7 of 49 because it comes out even. Well, it doesn't always happen that way, but here's one we could do. This means 7 to what power is 49? So that's 2. But how could we do that on our calculator? We can't directly, because it's not base 10, a common log, and it's not base E, a natural log. What we can do is this next note is called the change of base theorem, and we can take the log of the argument over the log of the base. I want you to check that on your calculator. Make sure you close your parentheses to finish that off before you hit divide. Let's check that and see if you get 2. All right, so log of 49 divided by log of 7. Okay, check that on my calculator. Again, it should work. That's that last line, and it always does. If it's not a base 10 or a base E log that you can directly do with your regular buttons, we do what's called, again, the change of base rule. It's called change of base, actually theorem, and it says you take the log of the argument divided by the log of the base every time. So let me give you one to try. And you could do, by the way it's written, you'll see in your book or in your notes, you could also do the ln. So the log of any base, but just be consistent. If you're going to use log log, use it on top and bottom. If you're going to use ln log, use it on top and bottom. And it'll work out either way. It could be any base log. It works for any base log. That's why the theorem is written like it is. But we really only have two main buttons, easy buttons to use on our calculator. So you'll either do probably base 10 or base E. But the general theorem says it could be any base. All right, so here's one to try. Again, make sure you're doing these from home on the other side of the screen and pausing as needed. I want you to do log base 3 of 42 and also log base 7 of 0.02. So again, the way we'll do this is the change of base log. Log of 42 divided by log of 3. That's how we would calculate that. So I'm going to have to type that in myself as well. And I am getting 3.402-ish, about 3.4. And the way we'll know if that makes sense is 3 raised to that power equal to 42. You could check these. 3 to that power should be 42. All right, so let me check. 3 raised to my last answer, and it works out. Okay, again, here we're doing it again. Log of the argument part divided by log of the base, log of 7. Type that on our calculator, log 0.02. I have to talk out loud to myself, maybe. That's not helping you. Divided by log of 7 is negative 2.010. So about negative 2 for that. All right, and again, that's called the change of base theorem. We can also use that for graphing. If I were graphing y equals log base 3 of x, to type that in my graphing calculator, since it's not base 10. Now some may see the subscript in math. Sometimes there's things in math, so you might find the subscript to use in your catalog. You can also do just the change of base theorem. For me, that's just about as easy. Type it as y equals log x divided by log 3. So type it using the change of base rule. So check that out on your graphing calculator. If it's not base 10, you need to fix it some way, either be able to type in the other base. You can't just type in log x, because that would be log base 10 of x, a different problem. All right, so that's one way to get it in your calculator. Also, if you were making a t-table, you could plug in things for x, calculate this out, and figure out t-table values. But graphing on the next page, since we're there talking about that, I have another video with more graphing examples on it, but I do want to just mention it here in your notes whenever we're doing a log function. So on your notes, I have a reminder how the exponential function looked. And then the log function is everything exponential reversed. The x and the y switch places, since the log is the inverse of the exponential. So the log graph looks like this. It goes through the point 1, 0 as its pivotal point. The y-axis is an asymptote. The domain is 0 with a parenthesis to infinity, just this part. And the range goes up and down without bound. And then we can use the shifting rules on that. So it looks like this if it's an increasing function. If you have log of a base greater than 1, for example, log base 3 of x, it's increasing on the whole domain. If it is a fraction base, like log base 1/3 of x, it's a decreasing. Just like it was with the exponent, it flips it around like that. It still has the pivotal point 1, 0. It still has the y-axis as an asymptote. The domain and range are the same, but it's flipped this way. So if you put your marker on it, your pencil on it, it's a decreasing, negative slanted, any place, any point along that curve, a decreasing function. All right, so that's all listed in that review there. And then shifting rules as well. I think this is a good place to pause to finish up those two topics. We'll come back in on the next video and talk some more.